Okay, so how to apply some of the stuff that we learned in the last. So first off, how do sampling distributions for proportions specifically change when we're looking at a sampling distribution versus a sample distribution? Well, first off, let's just look at an example, right? So here we have two simulations for the proportion of Reese's Pieces that are orange, drawn from a population, right? Each one of these simulations was run 400 times. The proportion each time varied. The true proportion was 0.15 for each population. The only difference between the two distributions is that this one had a sample size of 25 and this one had a sample size of 50. So basically each time this experiment was done, 25 Reese's Pieces were taken and they counted how many were orange out of the total. And with this one it was the same but with 50. Now if you look at the distributions, hopefully you're able to notice a few things. First of all, they both have the same center. They both are centered at 0.15. The true proportion, or the true population proportion, the population parameter, if you will. So that's a good sign. Notice that they are both approximately normal. That's a good sign. Since they're both centered around the true proportion, the average the average proportion of candies that were orange is centered around the parameter of interest, and they're both normal. The only difference between the two is that this one has a lot less variability than this one. If you notice, the one on the left, the one with the smaller sample size, doesn't go as tall as its counterpart, even though they have the same number of samples each time, and it is a little bit wider. It is a little more spread out, whereas this one is a lot narrower. It's a lot more tightly bound around mean here. The range is even smaller. This one, the range only goes from a little bit over 0 to a little bit less than 0.3, whereas this one goes from 0 all the way to 0.35. So the variation, the standard deviation, got smaller when they increased the sample size. And we saw that on the demonstration in the last one when we were looking at random distributions. So what does this mean for us? Well, first of all, it means that our sample proportion is an approximation, and it's calculated by taking the number of things in your sample that fit the criteria you're looking for and dividing it by your sample size. In some cases, a sampling distribution can be approximated by a normal curve. Of course, this will depend on the sample size and the population proportion. We noticed that the mean of the distribution is right at the parameter p. That suggests to us that the statistic p hat is an unbiased estimator of p. We talked about what qualifies as an unbiased estimator in the last presentation. And last, we noticed that not only based on this, but also based on our own visual evidence, that for any specific value for p, the parameter for the proportion, the standard deviation gets smaller as n, the sample size, gets larger. So essentially, the value for the standard deviation of the population proportion depends on both the sample size and the population proportion. So, what type of random variable would the population of a proportion be classified as? Well, let's think about it. It's essentially a binary scenario because if you're trying to find what proportion of a thing fits a certain criteria, it either does or doesn't fit that criteria. So you have a binary scenario. Most of the time, you have independent trials when you're trying to find the proportion of a thing. Usually the criteria of some item in a sample doesn't depend on any other item in that same sample. Unit, that was the word I was looking for. We know N, the sample size beforehand, and we know P, proportion, probability that any one unit from a population fits our criteria. So this makes this a binomial distribution. So what are the mean and the standard deviation for a binomial distribution? We know that the mean for binomial is given as N times P. Now for a sampling distribution, we know that we're going to take our sample and divide it by the number of items in that sample. So the mean can be calculated by N times P divided by N, which is just going to give us P. So that means, this seems like common sense at this point, but the mean for a sampling distribution of a proportion is going to equal the population proportion. In other words, P hat gives us an unbiased estimator of P. Now for a binomial distribution, we know that the standard deviation was given as N times P times 1 minus P, all underneath the square root. Now if you're going to take that and divide it by N, you could just divide it by N after the square root, but if you simplify using some algebra, you'll see that it can also be calculated by the square root of P times 1 minus P divided by N. So the mean for a sampling distribution for proportions is just given as the parameter P, it will equal the parameter P, and the standard deviation for a sampling distribution of equal, instead of the square root of N times P times 1 minus P, it'll be P times 1 minus P divided by N underneath that square root. Basically, as sample size increases, the spread is going to decrease, which is what we saw before. Here's a short version of what I just said. As I stated, the mean of the sampling distribution for P hat is just going to be the parameter P, and the standard deviation for P hat is just going to be the square root of P times 1 minus P over N. And this is as long as the 10% condition is satisfied. If you recall, the 10% condition means that the sample size has to be less than or equal to 10% of the overall population. Now, as N increases, the sampling distribution becomes approximately normal. Before you perform normal calculations, though, if you're going to approximate using a normal curve, you should make sure that the normal condition is satisfied. The normal condition states that you must have 10 successes and 10 failures in order for something to be approximated using a normal distribution. Now, usually in this scenario, we would approximate using a binomial. However, since the mean for this is just P and the standard deviation is P, has N as a denominator rather than in the numerator, then we will be approximating using a normal distribution whenever we are doing any calculations with a sampling distribution for proportions. So we do need to make sure that this condition is satisfied because we will be using a normal distribution. And if it's not, if we don't have at least 10 successes and 10 failures, then proceed. And there you go. That's everything there is to know about sampling distributions for proportions. Next one will cover means. Hope this was helpful.